Essas regiões podem ser tipo lineares.
Depois eu te conto.
Okay.
Mostly there or on the project?
No, I'm mostly on the slides.
A bit further.
You'll tell me.
I think it's not.
I see that people are still. Okay, so good morning. Let's start. Remember quantum mesoscopic physics of photons, but we were mostly discussing electrons. And today we will follow that path, which means that today I will try to prove some of the statements that I showed yesterday. So I gave you results, which I hope you still think are surprising. And today I wanted just to give a way to understand and to prove them. So we will be busy, again, mostly with electronic systems, also waves, but not too much with atoms. But tomorrow morning, I can really promise to you that we will discuss atoms and interaction photons and atoms ad nauseum. Okay? So that's the deal. Okay, so let's go. Let's start. So you remember all the themes, all the ideas that we developed yesterday, and one of them was about the coherent effect. Whether do they survive to disorder average or not? And you remember that, in fact, disorder average kills some of the phase coherent effects, like this phi-zero Webb Aronoff-Bohm effect, but it replaces it by something else, which is also a coherent effect. Okay, so this is what we learned from yesterday. And then I started to give you some general picture about those many Feynman passes, each of them associated to possible multiple scattering of paths of the wave in the scattering medium. Okay, so this is what you see here, two such trajectories. And we wanted to know what is the incoherent contribution and the coherent contribution. So I'm now following this idea, but in more details. So the quantity that I want to calculate is something that is called the quantum probability, but basically is this intensity that we discussed yesterday. And this probability or intensity, so this is a more technical object. This is the probability, the quantum probability, to go from one starting point R to an end point R prime by summing all the possible trajectories. And we know that the probability is just the square of the total amplitude. Okay? So this is just basic wave mechanics or quantum mechanics. You are with me here with this definition? So this is a basic object. Now what I can tell you is that if you know how to calculate the disorder average of this quantity, then you know how to calculate all possible physical quantities. So there are a few, for instance, conductance, we discussed it. Tomorrow we will see superradiance and Anderson phase transition and all this. If you know how to calculate this, you can say everything about anything. The problem is that usually it's difficult to calculate this object. Okay? A is the amplitude. This A, this is what you mean by A. This is the amplitude associated to a given path. And there are many, many passes, and you have to sum over all the possible multiple scattering passes. And this is the quantum amplitude. You see here it's just a complex conjugate of it. It's the quantum amplitude of each path to go from R to R prime. Okay? Of course, I don't know how to write it properly, but it exists. Okay, so this, by definition, what is written here, I can write as the sum of two terms. Terms for which I is equal to J, which means identical amplitudes, trajectories. And you see that if I is equal to J, then this is what we obtain. And I different from J are all the amplitudes that differ. Okay? And now the product of two different amplitudes, like this is the argument that we saw yesterday. This involves a phase shift. And this phase shift, which is the difference of lengths between two different amplitudes in units of the wavelengths, usually this difference, this phase shift is very big, and therefore on average it is zero. Okay? This is why this term can be safely taken to zero. Okay, so this is exactly the same argument as that I told you yesterday. Okay, and so now I just want to draw this result with pictures. And this is the picture. If we have now two identical trajectories, J and the J complex conjugate, which means they are the same, I is equal to J. This is the incoherent contribution. And for two differing multiple scattering amplitudes, the phase shift is large, and this vanishes on average. And this, if we retain only this, what we are doing is to describe incoherent propagation of the wave. Okay? And this incoherent contribution is very important. For instance, even, if we look at the propagation of the light through the clouds, okay, it's multiple scattering. Well, in Brazil, you don't have a lot of clouds, but but it's now there is, because it's spring or something like this, so we have clouds now. It's not just blue sky. But if you have clouds, then, or just the atmosphere, the multiple scattering of light through the atmosphere is completely governed by this incoherent propagation. And what we say is that the intensity just obeys, is described by this. There is no coherent effect.
So that would mean that the other term is the coherent?
And all the rest is coherent. All what is not completely incoherent, it has some degree of coherence. And all the lecture today will be just to evaluate this, to go beyond this crude assumption. This important but crude assumption. Okay, so this you remember that we discussed this speckle pattern. Before averaging, we have full coherence. And when we average over disorder configuration, most of the contribution vanish because of large phase difference. And if you think of this atmosphere, why do we don't see a speckle? Just because the scatter, they move, either in the clouds or in the atmosphere, and this realizes this disorder average, and therefore we are left with this incoherent term. Okay? So I'm saying many times the same thing, but there is a famous sentence by Felix Bloch, you know, from the Bloch theorem, that says something like, I think the translation is perhaps not easy. You should never underestimate the pleasure that you have to hear something that you already know. Okay, so I repeat things, and then you say, but this I know. So just enjoy listening to something that you already understand very well. Okay, so now I just want to propose to you a new design, and this is the design. When I have two multiple scattering passes that differ, I write it, I just draw it that way. And this vanishes upon averaging, and what remains are only those coupled identical trajectories that are coupled, and the probability that I was defining before is now the classical probability. So this is this index CL, and this is just given by this. And this, as a name, it is called this excitation, this way to propagate a wave through multiple scattering is called a diffusion. A diffusion, it's like a magnon or a phonon or a photon. It is an excitation of your system. Okay, it is a Goldstone mode, and this is, it has a name. It's called diffusion. Okay, in the literature. And why is it called diffusion? This guy, because you can show that to a good approximation, this excitation obeys a classical diffusion equation. The diffusion obeys a diffusion equation. Diffusion equation is this equation. Okay, so this means that the classical probability here, so here it's the time-dependent classical probability, obeys the Green's, it is a Green function, and this obeys this diffusion equation, which is the Green's equation of this propagator. Okay? You know what is a propagator? Green's functions of given differential equations and all this. And if you write it in Fourier transform, then you get something like this. And there is a coefficient that shows up here. And this is the diffusion coefficient. And this diffusion coefficient is related to the characteristic of the wave. It is equal to the group velocity of the wave, Vg, times the elastic mean free path. You remember that what describes the scattering properties of the medium, divided by 3, and 3 is just a dimension of the space. So here it's written in a 3-dimensional space. In a 1-dimensional space, it would be 1. Okay? So the way that a wave propagates in multiple scattering system incoherently is governed by diffusion equation. So the intensity of light through the clouds is diffusive. The photons in a cloud of atoms, cold or hot or whatever, is diffusive. Electrons in a metal behave diffusively, which means the square of the wave function obeys the diffusion equation. Everywhere that you have a wave that is subject to multiple scattering, the incoherent part obeys the diffusion equation. Okay? It's absolutely universal. No exception. Magnetization in a disordered system obeys diffusion equation. Everything. Okay? So, what does it mean? It means that if you have here your scattering system, you have your wave that does the diffusion. So diffusion is is a random walk. Diffusion is a continuous version of the random walk. And this is this probability. So this is your system of size L, typically. The path length between two scattering events is the elastic mean free path. And if we are in the multiple scattering regime, elastic mean free path is much smaller than the size of the system. And this is your random walk of the light, of the wave, of the electrons, of whatever. Okay, so any random walk or diffusion process can be characterized by this expression, which tells you what is the variance of the cloud of this motion of the particle. And this variance is proportional to the time t, and the proportionality constant is the diffusion coefficient times twice the space dimensionality. Now, out of this equality, which is well known, do you know this equality? That the solution of diffusion equation, if you look at the spread of the particle, it is given by this. Do you know this? So this average here is just defined by this. So you have a probability, which is this classical probability that I wrote, okay, as a function of t and of everything. And if you calculate now, and it depends also on r and r prime will be, so r will be the starting point. Now, if you integrate over the whole volume and you calculate r squared, this is r squared that is defined here. And the result is that this is a function of t, because this depends on t. And this is proportional to t. And this is the result. Okay? So now, out of this equality, you can define a characteristic time, which is called the tauless time. And this tauless time is the time that it takes for this diffusive wave to cover the whole system, which means for which r squared is equal to L squared. Okay? And this time is called tau d, like tauless. And it is defined that way. If the time is much smaller than this tauless time, then your random walk is just very much localized into the system. But if you are at times which are much larger than this tauless time, in fact, you cover by random walk the whole volume that is accessible to the wave. Okay? So this is the tauless time. Tauless, you heard about tauless? In which context? For those who heard about him? Huh?
The tauless, the phase, the transition.
Phase transition, yes. The Berezinski-Kosterlitz tauless transition. This is the same tauless. For the aficionados of topology, there is this TKKN work on the quantum Hall effect that shows that the quantum Hall conductance is quantized in units of e squared over h times an integer. This is tauless, Nightingale, Komoto, and Denise. This is the same tauless. And tauless was also one of the founding fathers of mesoscopic physics. And this is why this time bears his name. Although most probably the grandfather of tauless knew about this time. And this is what tauless once told me. Told me, you know, I'm very honored by this, but probably my grandfather knew about this. So it's nothing new here. Okay, so this is called the tauless time. And now let's put all this on a graph. So here we have 2 times now. We have, so this is the time arrow. So we have the elastic time, which means the time at which the first scattering event takes place in a system. and then we have this tailless time. So for times which are smaller than the elastic time, you don't have time to make your first scattering, so your system is ballistic. After this time, you experience multiple scattering, so you are in this diffusive regime that we just discussed, okay? And after this tailless time, you are in what is called the ergodic regime. Ergodic because here, physically, you cover all the space that is accessible to the system, okay? So this is an ergodic limit. And now yesterday there were 1.5 questions related to this ergodic limit, and I said that I don't want to dwell too much into this. So this is a little bit of dwelling into this, but I will discuss this later on. And there is another time that we discussed yesterday, which was this phase coherence time. This phase coherence time marks the limit, the border between what is called the mesoscopic limit, in which you may have coherent effect, yet to be discussed, that we discussed yesterday, and above, for times which are larger than this phase coherence time, then you have the classical limit, where all coherent effects, if they exist, are washed out. Okay? So those are the typical times of our systems. You are with me? Yes? You don't seem to be completely with me. I see some floating around here. Is it true? Some, I'm with you, yes, yes. No? Okay, yes.
How do you define this elastic time? Just like
This is the elastic mean-free path in units of the phase of the group velocity that I just defined before. Okay? So the elastic mean-free path that we defined yesterday is just the group velocity times this. So E is for elastic. Okay, so now I described this coherent, incoherent limit, and I want to come back to my coherent effects. So what is the first correction to incoherent contribution? So you remember with our new design of multiple scattering passes, we said that we keep these, which are diffusons, which are those Goldstone modes, and they are extremely important, they are extremely interesting, they are everywhere, and we neglect all of them because dephasing is too big. Okay, this is what we said. And even we agreed on this. And now I ask, what is the first correction? Meaning, what is the smallest phase shift that I can still keep? And to say, you know, this does not disappear. So is it possible to address this question? To say it again, I neglected all possible coherent effects beyond this incoherent by saying, on average, they are all zero. But my argument was true, but crude. I said just, you know, if you have this phase shift in units of lambda, it will be very large, and then it is zero. But probably there are phase shifts, there are multiple scattering passes for which the phase shift is perhaps not that big, and perhaps I can keep it. Okay, so this is the question that I try to formulate. Is it possible to say something about small phase shift, bigger phase shift, etc.? And
just to clarify something that I'm confused, like you're saying that as for which the phase shift they are coherent.
yeah, all the other terms that I neglected, they contain coherence.
But how? Like, they have a phase shift. They shouldn't be incoherent.
No. No. There is a phase shift, but I keep this phase shift. Okay, so this contains all the information that I have about those Feynman path integrals, and I make the sum. So if I throw out all the phase part of it, I keep only the phase independent part. So I have this diffusion equation, which is purely classical. All the rest, you know, if I keep some information about the phases, then I remember that I have waves that are doing multiple scattering. Because in this incoherent contribution, I can say that this is wave, but this is the intensity of the wave that does it. So it's like a particle. There is no quantum mechanics information or no wave information in this, okay? And I want to see if it's possible to quantify this, this phase shift. And it is possible. But I will, so you can do it in two different ways. One is extremely complicated, and one is extremely simple physically, but requires a given amount of how to say, of belief, of faith in what I'm saying. Okay, so I will tell you what is the smallest phase shift, and you can say, well, I don't understand, so you say it, good. Then you have no other choice than to go, for instance, to our book and to complete information, or to believe what I'm going to tell you. So the smallest phase shift is when amplitude passes cross. Yes, sorry.
Just to make a clarification, when you try to make a line from R to R prime, it's a path from R to R prime, right?
I worked on it. Look. I lost it.
But the dashed line, what represents, what's the difference between the dashed line and the...
Okay, you see, the main line here is what, so this probability, by definition, is the product of an amplitude and the complex conjugate of an amplitude, like any probability in quantum mechanics.
Oh.
And this dashed line represents the complex, complex conjugate amplitude. So you see it's J star,
So it's
and it's J.
probability of the path.
Sorry?
It's probability of the path.
It's a probability of the path to go from R to R prime, and this is just this incoherent one. And here it is, again, a multiple scattering path, and it's complex conjugate. Why? Because in the definition of P, I have A times A complex conjugate.
Another path.
Yes. Okay? No. The star is not because it's another path. The star is because the probability is the product of an amplitude times a complex conjugate of an amplitude. Okay? Good. I'm here again. So here is an example of classical diffusion. So those are two diffusons, two of those incoherent modes. Okay, so this is classical. And now I claim that the smallest phase shift that you can achieve is obtained when you have such a crossing that you start with two diffusons. So all this is purely incoherent. You end up with two diffusons, which are incoherent. So you see there are passes that are identical, but somewhere in space, they exchange their amplitudes. You see this? So here we had green, green, red, red. And at this point, this green goes with the complex conjugate of the red here, because it has to be an amplitude and the complex conjugate. And this red goes with the complex conjugate of the green. So this is a quantum crossing. It is called a quantum crossing in literature. So you have to think of it as a diffusion is like a DNA molecule. So you know that DNA molecule is made out of two strands of molecules. And so those two strands, they are just associated in a diffusion. So it is phase incoherent. And at some point, I just open it and I couple it differently here. And then I built two other DNAs, which are diffusons, and they propagate. And they are phase incoherent. You understand this, what is written here? Yes? It's nice, even?
I still don't understand what you're trying to represent when you separate the strings of the complex conjugate path and the regular path.
Here. This was the definition. I want to calculate this probability. This probability, quantum mechanics or wave mechanics, it is defined as the sum over all possible multiple scattering trajectories of an amplitude times the complex conjugate of another amplitude. So do you agree with this definition?
In that sum, I and J are indexes for different paths.
Yes.
So if I and J are different, it means that you are multiplying a complex conjugate of a different path.
Yes.
Okay. Then
This is just the definition of the quantum probability. You have a wave function associated to a path, another wave function associated to another path. If you want the probability, is psi times psi complex conjugate. But then now, it is for all the possible passes. This is this Feynman path representation. Okay?
Okay. Now, another question. The sum where I differs from J contains
A phase.
contain paths where
Which are different.
yeah, but they are the same. Imagine that both are following the same path, and then one makes a loop, and they keep following.
Yes, they differ.
They would be different. But,
Yes.
That should not cancel in terms of probability.
No, they exist. This is true. That what you are telling me, you say you have a path like this, and you have another path which is exactly the same, but does like this. Yeah. This is what you had in mind, right? Okay, so you see that there is a phase shift between the two. The phase shift is associated to the fact that the length of this and the length of that, they differ by this. And the phase shift will be this length in units of wavelengths. And this length in units of wavelengths can be very large. Now, if the loop is very, very small, then it will be very small. Okay? This I agree with you. And this is counted in the terms that I neglected. But now I try to go along your way and to say, is it possible to find the smallest phase shift that contributes, which you think is this one, but act of faith that I required from you is that, no, this is not this one. This is when they exchange passes the way that I presented. Okay? But this is a good idea. But it's not exactly the right one. Okay? Other questions? This quantum crossing is, you cope with it? Okay, so this is the smallest phase shift, I claim. And again, I can prove it, but here I just require that you agree with me. Now, the occurrence of such a quantum crossing after a time t, so you have two waves that go into the multiple scattering in the scattering system, and after a time t, the probability of occurrence of such a quantum crossing, again, I give you the formula. It's a simple formula, but it's difficult to show it, but the result is simple, is given by this. So the probability of crossing after a time t depends on the wavelength, depends on the space dimensionality, depends on the group velocity. So here I put c because it's light. I like to use light from time to time. Time t divided by the volume of the system. And this is the idea that you have this DNA incoherent guy. And why do we see here lambda? Because this is the cross-section of this diffusion. And the length of it is controlled by this guy, which is here in terms of electrons, it's Fermi velocity times tau. Okay, so the time spent by such a diffusive photon, so now I'm with photons, is this tauless time in a given volume, in the ergodic limit. I wait, okay, in enough time. So the probability to have a crossing when I cover the whole volume of the photon that is diffusing is just this expression, where now T is equal to this tau less time. So I just put T equals to tau less time, which is L squared divided by D that we defined in the ergodic limit. And this probability for having a quantum crossing is just this combination. And this combination, by definition, I call it 1 over G. So this G is a dimensionless quantity, because the probability is dimensionless quantity, okay? And I call it 1 over G. And this is a result. By the way, it's not just hand waving. I can show you good calculations of propagators, of Green's functions, and everything that you want, okay? Diagrams. So this is the end result, and this is 1 over G. Okay, so what is this G? This G now I replace tau D, tau less time, by its expression, and G is just the inverse of this. It can be written as the diffusion coefficient because of this, divided by the group velocity of the wave, lambda to the power D minus 1, L to the power D minus 2 because of this L that is here. It's a beautiful object. Do you know this object? Physical, can you give a name as a physical quantity to this object? You can, but you don't, you are shy. You don't want to say it. So I will help you. First of all, we saw it yesterday already, this object. So let's just look at it and go further. First of all, let me again explain what we have been doing. Here, what you see is the diffusion. Diffusion means that you have a random walk of the intensity of the wave. Okay? So in a random walk looks like this. You have many crossings of the random walk with itself. There is no quantum crossing here. So those crossings that you see here or here, they are not quantum crossings. Quantum crossings is when you have something like this, which are two diffusons, and from time to time you see that they exchange their amplitudes in such a quantum crossing, and this is what is governed by this probability that I called P cross. Okay? The volume of such a crossing is what we calculated already in some sense, is lambda to the power D minus 1 times the elastic mean free path. Now, what I announced already is the following, is that those quantum crossings, they decrease the diffusion coefficient, which means that they slow down the diffusion of the wave. Or if you prefer, they localize the particle. The particle wants to diffuse with the diffusion coefficient. You remember that R squared, which is the spread of the wave packet, is proportional to T, but also to D. If D goes to 0, then the wave does not propagate. This has another name. It's called localization of the wave. So what I already tell you is that those quantum crossings, they are this is the mechanism that gives rise to Anderson localization. When there is a proliferation of quantum crossings, your wave stops, does not propagate, and you have localized phase. You have Anderson localization. This happens for a given amount of disorder. We will discuss it later today and at length tomorrow. Okay? But I already tell you this. This is when we have only those quantum crossings, we call it weak localization. When we have proliferations of those quantum crossings, we call it strong localization and Anderson localization transition. Okay. So now, what is the physical meaning of this parameter G? Because it looks that this is an important parameter. This is the parameter that controls those quantum crossings and will eventually lead to Anderson phase transition, something extremely dramatic in the system, right? So what is the meaning of this parameter? So yesterday, this is something that I showed you yesterday. We discussed this electrical conductance of a metal. And then you all told me, or you agreed with what I said, that a metal can be modeled as a quantum gas of electrons scattered by elastic disorder. And classically, the conductance of a cubic sample of size L to the power D is given by Ohm's law, which says that the conductance is proportional to the conductivity times this dependence on the size of the system, L to the power D minus 2, where D is the space dimensionality. Remember that we saw it yesterday? And I wanted to write it in a more down-to-earth way, and you said, no, 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 don't do it, we know. You remember? So this was yesterday. So now look at what we wrote. We wrote this expression for G, just before. And here I replaced the diffusion coefficient by its expression. So you see that diffusion coefficient was this c velocity divided by 3 because of the space dimensionality. So d, this should be d here. But OK, it's 3. And in fact, what is this combination that we wrote? It's simply the classical conductance that is here divided by E squared divided by H. So this object, which is this object divided by this, is a dimensionless quantity, and it's called the dimensionless conductance. So what controls quantum crossings is a quantity that is just the dimensionless electrical conductance. Is it nice? You like it? You like it? Say it. I mean, don't, yes, it's nice, it's beautiful. We just, from completely different argument, approach, we just look at this quantum crossings and all this, we arrive to the fact that with diagrams and with everything, that this probability of quantum crossing is driven by a dimensionless parameter. And it happens that this dimensionless parameter, in the context of electrical conductance of a metal, has a meaning. It is the conductance in units of E squared over H, which is the natural unit of quantum conductance. And this is this G. I said that the conductance, the natural units of conductance is E squared over H. Is it correct? Did you know this? That the units of quantum of conductance is E squared over H? The combination of E and H, E squared over H, is a conductance. Do you know another unit of conductance, which is not quantum, which is purely electromagnetic? Huh? Zeeman? No, not unit, from fundamental constants. Something that is called the impedance of an antenna for electromagnetic waves. It's the square root of the ratio between epsilon 0 and mu 0, the permittivity, dielectric permittivity and magnetic permittivity of the vacuum. This is also a conductance. Okay? So one is quantum, this one. The other one is electromagnetic and not quantum. It's the impedance of an antenna. You know this? You know what is the ratio of those two conductances? It is a dimensionless constant. And what is the name of this dimensionless constant? You are with me? You follow what I'm saying, or I lost you? There is a quantum unit of conductance, which is this E squared over H. You have another one, which is called Z0 in the literature, but it's also it's an impedance, which is this epsilon 0 divided by mu 0 square root. Now, the ratio of those two is dimensionless. So what is this quantity?
1/137.
It is called the fine structure constant. Yes, the fine structure constant, alpha, that drives the interaction between matter and electromagnetic field, photons. It's called the fine structure constant. This is the ratio of those two conductances. And this is small, 10 to the minus 2. Okay? Which means that quantum effects are much smaller in amplitudes than electromagnetic effects. Okay? So this probability, this crossing probability, which is driven by this G is the classical conductance in units of E squared over H. But this can be defined for whatever, for electrons, but also for waves. Here, there is no E squared over H. This depends on multiple scattering of your waves. Okay, so now that we notice this, there is a direct consequence, which is quantum corrections to electrical transport. So yesterday, I told you something that the coherent effect that we discussed, they are in fact universal. So they do not depend on the disorder, on things like this. I told you this, but I said that today, I will show it. So here is the moment that I give you a hint of this. So classical transport is driven by this classical conductance. Classical conductance, it is this parameter G times E squared over H, where this parameter G is large, because conductance is large. Now, quantum corrections, what do they give to me? They are given by the classical conductance times this probability to have a quantum crossing, which is proportional to 1 over G. This is what we saw. So this is quantum corrections. They are equal to G classical times this quantum crossing, which is 1 over G. But G classical is proportional to G, which means that all that what depends on the characteristic of the system, elastic mean free path and whatever, will disappear because this G cancels with this 1 over G, which means that all quantum corrections will be always universal, independent of the detail of the system. It does not depend on the size of the system. It does not depend on the elastic mean free path. It does not depend on the wavelength. It depends on nothing. Just E squared over H. But this is not so easy. In fact, so this is what I just say, that quantum corrections are universal. They are independent of the microscopic disorder. But here, there is the almost equal to. So it is proportional to E squared over H, but times something. And this something here is a number, because everything is dimensionless here. It's just a number. But this number is essential to the theory. In fact, all the sport of mesoscopic physics is to be able to calculate this number here. Just a number that depends on many things. And it is very difficult to calculate this number, but it's very important. And if you want to obtain a precise value for this number, then you have to work, and this is what you have to do. So I gave you, very simple and nice hints and all this, but at the end of the day, if you want really to calculate things in whatever system you want, where there are coherent effects, you need to do very hard field theory. There is no way out, okay? And this is just a few diagrams that you have to calculate. I will not tell you what it is and all this. Just believe me that it's extremely difficult, and it took decades to people to calculate all those corrections, okay? But they are extremely important because I told you yesterday that mesoscopic physics is as precise as QED. In order to calculate QED corrections, you need to sum up also many diagrams. This is why it ends up to be very precise, but here the same. You have to do exactly the same way. Okay? So it's not so as simple as I said, G, and everybody knows that it's this. You have to work hard. Okay? But it's interesting. So now I would like to make a short intermezzo based on this understanding of coherent effect that we just developed. Okay? So before I start this intermezzo, do you have questions about all what I said, which were a lot of information in a short time? Yes? to enhance transport? Well, so this we will discuss it tomorrow. Usually, for scalar waves or just electronic quantum mechanics, those coherent effects, they decrease transport. They don't increase transport. This is localization. If you want to reverse it, you need some other piece of physics. And tomorrow I will give an example of this for the superradiance of atoms and photons. But usually, no, it doesn't work. You just decrease.
What is spin orbit coupling?
Spin orbit?
Spin orbit coupling, it's may decrease, right?
Yes, so this is also an answer to what he said. So there is, yes, you can change localization properties by spin orbit coupling, absolutely. But I will not discuss this.
Yeah.
But you are right. It is exactly, I think, what he meant, yes.
So the simple the crossing you wrote corresponds to the 4-point function, the function in a 3 level, and the other diagrams are the 4-point functions in
Yes.
the
Yes.
level. Oh, okay.
Yes, we will draw it later today.
Okay.
Yes, so later today I will show you how you calculate those 4-point functions.
Okay.
But again, at the elementary level. But you are absolutely right. There are, yeah. Other questions? No, I can start with the intermezzo on conductance and all this. Yes? Sure, okay. So I want to discuss this quantum phase transition, this Anderson localization transition, in the framework of what I said. So now what we saw is that quantum corrections can be obtained as expansion in powers of this parameter 1 over g. Okay, we identified the parameter, which is a small parameter, 1 over g, and we can just make higher order expansion in this parameter. It's very difficult, but it's possible. Okay? Okay. And we can calculate quantum corrections to all physical quantities that we wish. So here is the expression of the diffusion coefficient, which is a physical quantity, when I sum up those quantum corrections. Okay? So this is an expansion in 1 over g, and you see that to lowest order we just have a constant diffusion coefficient, as we said. The first correction is indeed proportional to 1 over g, and this is the result of the calculation in 2 dimensions. And the next correction that you would expect would be something like this term squared. But when you do the calculation, what you notice is that this correction does not exist. It is 0. Okay? And this is not by chance. It is not a simple coincidence. It is an expression of something that is called scaling. Do you know what is scaling? Do you hear about notion of scaling? Yes, more or less. And so it is singular because it's an expansion in 1 over g, which is a small parameter, but this is times logarithm of the size of the system, L, divided by the elastic mean free path. So this term is huge because we are in a multiple scattering regime. So the logarithm of this is much smaller, but anyway, this diverges in the limit L, large L goes to infinity. So this is singular, okay? But when you see something like this in field theory, then usually you say something happens, something interesting happens. First of all, it tells us that d equals to 2. 2 dimensions is a kind of interesting critical dimension. And the second thing is that if we have this expansion as a log of something and that terms of the square of them is 0, it means that we have scaling, most probably. It's not a proof, it's just a hint. And now you can make renormalization of this. I will not enter into this. Either you know it what is renormalization and all this, and then you're happy. And if you never heard about the word renormalization in statistical mechanics and all this, then you will be unhappy during this short intermezzo. Okay? So once you do this renormalization, this change, you plug this d of L into the expression of G that we have, you see that D decreases. So we have, this is the incoherent part, and here there is a minus sign, so this decreases the size of the D. So which means the diffusion constant is smaller, and this means that the conductance here is also smaller. And this is what I said, that your system is less conducting, so therefore it is more insulator. Okay, so you see this idea that we are going from a very good conductor, metal, to an insulator, to something that electrons, they do not really move. Okay, and now what is the meaning of this scaling? So all this, in a nutshell, what I will tell you is the idea that is in this very famous paper by Phil Anderson and 3 others. It's called the Gang of 4 paper. It is not the paper of Phil Anderson that Jörg mentioned yesterday, and they gave as a working paper. It's another one, because Phil Anderson is most probably one of the most influential physicists in condensed matter physics at large from after the Second World War. He had really contributions almost in everything. And this, by the way, is not his main contribution. This orthogonality catastrophe is extremely important stuff, and there are many others in everything. Okay, so this is for Anderson, and the point is the following. The logarithmic expansion that you saw before means the following, that if you know G of L at a given scale, L, then you know it at any scale. And this is written here as a mathematical formula. And this is the idea of scaling. That if I know this, then I know G at another scale, which is here just stretched, this scale stretched by a factor epsilon L. And this is a function only of G of L and this epsilon. So again, what I wrote before, which is a result of perturbation expansion, the fact that this 1 over G log L squared term disappears, is not just by chance, is an expression of scaling, and scaling is this, is that if you know G at the size L, then you know it at any scale. So this is, mathematically it's extremely simple, but it's, such an important idea in physics that I really encourage you to go to take it and to scratch your head and to say, what the hell he wanted to tell us about this? So it looks really simple, but I don't understand. It's really a very, very important idea. Believe me. So now you can expand this equality that I wrote here for as a function of epsilon. Epsilon is small. And if you expand it, what you get is that this is equal to G of L times 1 plus epsilon beta of G plus something. And this beta of G is just defined by the logarithmic derivative of G with respect to L. It has a name in field theory. It is called the Gell-Mann and Low function. It happens all the time in quantum field theory. Now, you notice that, in fact, there is here an expansion to the power 1 over G to the power 5. So which means that all the other terms that are 0, I told you that are 0, we can show that up to the 5th order, they are all 0. This we know to show, but we don't know to show afterwards. This you have to work hard, very hard. Nobody knows how to do this, but you are welcome. It's very important to show this. And the scaling behavior is also expressed by the fact, exactly what is written here, is to say that G, which is an independent function a priori of the size of the system and of the disorder, here I call W just disorder, all the elastic mean free path, all of what we had, It's not a function of two parameters, but in fact, it's a function of one parameter only. And this is scaling. Instead of having a function, so you know, in thermodynamics or statistical mechanics, you do it every day, right? Right? Fermi, the free energy of a system is not a function of all the parameters, but just a function of combinations of them. So this is precisely what we have here. And this conductance is in fact a function of a single parameter, which is the ratio of L divided by something that must have the dimension of length, but depends only on the disorder. And this something is called, this length is called the localization length. Okay? And this is just a result, an outcome of this scaling assumption, which itself is a consequence of this expansion in powers of 1 over g, where 1 over g are quantum crossings. We did quite a lot in a few minutes. Okay? So it's difficult. I agree.
Could you repeat what's W?
I put in W all what is disorder. So if you remember the expression of G, it was a combination of the elastic mean free path and the velocity and all this. So all this, I call it W. Okay? So I don't want to have a... And by the way, tomorrow morning, I will give a precise definition of W because I will need it. But here, I don't need it. Just all what we wrote an expression for G, which depend on L and on other parameters when I wrote it. All the other parameters, I call it W. Okay? And this is a function only of this. So in the classical regime, this was obvious. But generally, it is not obvious when you do all those corrections and all this. So generally, it can be written like this. And this psi is called the localization length. But again, this is a consequence of an assumption which is very, very, very unusual. Okay, so here, for instance, is numerical proof, if I can say, of this scaling argument. So this is an old result from 1981 by Kramer and McKinnon. It's purely numerical calculations using the Anderson-Hamiltonian. I will not write for you today what is the Anderson-Hamiltonian. I will do it tomorrow, but it's not important here. So here it is this conductance in 2 dimensions, in 3 dimensions, and here each of the symbols that you have correspond to different values of W, which is disorder. And it goes from very weak disorder to very strong disorder, which means 1 over G corrections, just the first correction, to many, many corrections. And what you see is that, indeed, when you plot this function as a function of L divided by psi of W, all the different plots, they fall onto one universal curve, which is called the scaling curve. Okay? So this is the meaning of scaling. In 2 dimensions, nothing happens. You have universality, you have scaling, but nothing specific happens. But in 3 dimensions, you see that for the same Hamiltonian, you have a point here, you have a cusp. It's a singularity in this G. And this is the signal of Anderson phase transition. Here it's just numerics. You run, you calculate the conductance of this Hamiltonian, and this is what you observe. And this is just numerical proof that there is Anderson phase transition above 2 dimensions. In 2 dimensions, you don't see any singularity. In 3 dimensions, you see singularity. And the Anderson localization phase transition occurs in D larger than 2. Another thing. So it's a lot of physics, a lot of things. Now, we all agree that this phase transition, here I said I used electrons, but I can use waves, I can use whatever. This is universal. I will see exactly the same. For photons that propagate in a cloud of cold atoms, for electrons in metals, for sound waves in Amazonas forest. By the way, they were an experiment, not in Amazonas forest, but in Black Forest in Germany to see localization of sound waves. So this is a universal scenario of localization. Okay? It's true for any wave. Like it? I also like it very much. It's already many years that I'm saying this, you know, and we are not alone. There are many other people that like it very much. Yes.
Do you have an associated symmetry breaking to this transition?
Oh, this is a very good question. And the answer is most probably no. But, you know, I told you yesterday and I repeat it today, we don't know how to prove analytically, theoretically, that there is this transition. We just notice it, we observe it. And we have the scaling and all this. But there is no broken symmetry like in other usual phase transitions. It may be, but it's not obvious. Okay? But this is a very good question. I don't have an answer.
So as far as we know, even though it's not topological, it may not have a symmetry breaking.
Yes, but it's a quantum phase transition.
Yeah.
Yes. Now, because people are, you know, everything is recurrent in physics, there are a number of people that are interested in topological meaning of the Anderson phase transition. And yesterday, I must apologize to Philippe. When he was lecturing, I was reading a paper on that subject that I had to report on. So that's the point that, okay, a lot of things. This is the end of the intermezzo that I want to tell you. But tomorrow I will discuss again this Anderson phase transition from another point of view. How much time do you have? It's 20 minutes? Yeah, okay. So, but what is important is to get entertained, to enjoy what we are, not to finish. So now I'm coming back to weak disorder physics, which is the limit where you remember the wavelength is much smaller than the elastic mean free path, or it's the same, this parameter G is much larger compared to 1, or the probability of quantum crossing is extremely small. It's 1 over G. So this is what is written. The probability of a crossing is small. Phase coherent corrections to the classical limit are small. Now, as I said, quantum crossings modify the classical probability, meaning the diffusion. And the fact that the diffusion is a diffusing wave propagates to long distances. In fact, those quantum crossings, those coherent effects can be propagated over very long distances because you remember that you have this quantum crossing and then you have two diffusons that propagate those effects. Okay, quantum crossings are independently distributed. Well, this probably is not entirely correct, but okay. And we can generate higher order corrections to the diffusion as an expansion in powers of 1 over G. Good, all this is what we said. So now I will implement more in details this idea to the electronic transport and what is called weak localization. You are still with me? Not hungry? Yes? Good. So, Drude theory. So, Drude theory is the classical description of transport. Here I have given a slab. This is, okay, this is the limit of my conductor. And Drude theory is just a propagation of electrons. Classically, they obey a diffusion equation. So the only mode that we have is this diffusion mode. Okay? And this is what is represented in our new design by this diffusion. Okay? So this is Drude theory. Drude theory is just this picture. Okay? Now, we want to include the first correction to this. So we have only one diffusion. So it's a 2-point correlation function, not a 4-point. 4-point will come later to answer your question. It's a 2-point. I have this electron enter here, goes out here. And now I want to include a quantum crossing. So this is a quantum crossing. You remember that it exchanged the amplitudes. And now it's close to what you wanted, but not precisely. Look at what you wanted and look at what it is. It's not exactly the same. Okay? So, but it was a good hint. Good guess, sorry. And so you can calculate this quantum correction, and what you get is that the quantum correction to the classical conductance is just given after you do the calculation by the probability to have a closed loop here, and it goes with a minus sign, so this you have to calculate it. The probability to have a closed loop here, so this is the closed loop, as a function of tau d, which is this tau less time. So as you see, quantum correction decreases the conductance, and this is called weak localization. And this is always so, okay, for just scalar waves. So now you said that if there is spin orbit, it's not that because you were, you said that if there is spin orbit, you can change this sign. And this is indeed true. But without spin orbit, for scalar waves, there is minus sign. With spin orbits or other things, you may reverse this sign and increase transport, okay? But here you decrease it. And if you remember what I showed you yesterday I showed you this slide, and I said that coherent corrections can come either from coherent backscattering, this situation, or closed loops. And you see that in this case of weak localization, it comes from closed loops. Okay? So this is this closed loop. So this is the classical probability. Now, this is this first order correction. So this is the interference probability, which is proportional to 1 over g. But if now you have a closed loop, which means that r is equal to r prime, what you see is that if you put r is equal to r prime here, you get something like this. So this is a diffusion where the two waves go along the same direction. And this correction is now this, because r is equal to r prime, but you see that the two waves goes in opposite direction. But the two probability, the return probability, they are just equal, okay? They are equal if there is time reversal invariance. So here I'm going a bit faster. I noticed this. And the return probability is doubled. You get twice return probability, and this is precisely what we had yesterday. You remember that if R1 is equal to R2, this coherent term is 1, and we get 1 plus 1. This is a diffusion. This is this quantum correction, and 1 plus 1 is 2. And this is... this is this 1 diffusion plus 1 Couperon. Okay? So, in the presence of a dephasing mechanism that breaks time coherence, only the trajectories with t smaller than tau phi will contribute. And now I can explain and justify what I said yesterday about this Charvin and Charvin effect. You remember that we said that for the Charvin and Charvin effect, the periodicity is phi 0 over 2, and not only phi 0. You remember this? I see that I lost a number of people here. I lost you. Yes? You. No? You are still with me? A bit. So yesterday I said this, and now look, why is it true? So this is this Couperon that we just wrote, okay? So suppose that you put now Aronoff-Bohm flux, exactly what we discussed yesterday. You see that one trajectory, the plane one, it encircles the flux, and therefore it gets a phase which is 2 pi phi divided by phi 0. But the time reversed trajectory has a phase now which is just the opposite because it is time reversed. And this is minus 2 pi phi over phi 0. And now the phase difference between the two is twice this because it is this minus this. So therefore it is this plus 2 pi phi over phi 0, and therefore the total phase is 4 pi phi divided by phi 0. And therefore you get a phi 0 over 2 periodicity. This is beautiful. It's very quick. I can see this, but it's beautiful. Now, if you write the equation for this interference probability, you get a diffusion equation. So you recognize here the diffusion equation, but here it is a covariant diffusion equation with a charge here because of this effect, which is twice the electron charge. And I write this because this is because of this effective charge, which is 2e, that this mode, which is a correction to the diffusion mode, is called the Couperon mode. I used the term Couperon, but I did not justify it. So did you know some BCS theory about superconductivity? So the BCS superconducting instability, it is called the Cooper channel. BCS, Bardeen, Cooper, Schrieffer. Cooper, this is the Cooper. And this is because of this Cooper channel that, in fact, in superconductivity, the important charge is a charge of a pair, Cooper pair, which is 2e, and not just single e. And here, when people discovered all this mechanism in the 1980s, they ended up with this 2e. And they said, most probably it's the same instability as in superconductivity. And therefore, we will call this new excitation a Couperon. So it's like a Goldstone mode, but it's another mode. This is this 1 over G correction. And they called it a Couperon because of this. But now we know that this has nothing to do with the Cooper channel. It has to do with 1 over G corrections. But the name remains. It's called the Couperon. Okay? Well, myself, I'm tired to all this information. So here is now a summary of what I said. So yesterday we discussed the Webb experiment and the Charvin and Charvin experiment. So the Webb experiment is on a specific realization of disorder. And there, so we had this Webb ring, and this ring, you see that you have possible trajectories. You have a trajectory that goes that way, a trajectory that goes that way. And when you look at the phase difference here, it encircles a phase difference which is just 2 pi phi over phi 0, and therefore the conductance associated to this oscillates with period h over e. Only h over e. This is just this Aronoff-Bohm effect. When you average over disorder, this disappears. But when now you take into account those Couperon 1 over G corrections, the new mechanism is precisely what I explained to you now. It's the quantum crossings. So you have waves that do complete circle around here, another one that do a complete circle in the opposite direction, and they have a quantum crossing here. And the phase difference now is 4 pi phi over phi 0, and this oscillates with period h divided by 2e, and not h divided by e. This is this 2e, which is this Cooper pair of Couperons, but this is associated to quantum crossings of waves that are going twice around the ring. So you see the difference between the two? So this disappears, the upper one, when we average over disorder. This remains because of this small quantum crossing. Yes? Yes?
But in the drawing, you have quantum crossing of the same path, and you say that it will not collaborate. I think.
This one? No, this is exactly the same as this. This is exactly the same. You have two waves, and they do this quantum crossing. This and this are the same. Exactly the same. Okay? So, back to coherent effect for light. So this is a bit less than 10 minutes is okay. So now, you remember that we saw this yesterday? We said that there is speckle patterns in optics. Now we're in light, only for light. And we have this interference picture. And now I want to describe this using this quantum crossing picture, but for waves, for photons. And you remember what I showed yesterday, that if we average this speckle pattern over all possible realizations, we get this coherent backscattering. Okay, so this we saw. And now I want to discuss the fluctuations and correlations. This will be tough a bit, but this is a game. You will see. So now let's see if we understand all the idea that we have been discussing today. So we have, this is our slab. Photons are entering here. They are going out here. A means an angular direction. A is for polarization epsilon A and incident wave along wave vector SA. This I call it A. This I call it A prime, B, B prime. So this is the meaning that we have here, okay? Now, I want to calculate the intensity that is transmitted, which means the transmission coefficient. The transmission coefficient is an amplitude, complex amplitude square, quantum mechanics, what we discussed earlier. But now, what I want to do is to calculate fluctuations and correlations of those fluctuations, which means that I'm not interested in this guy, I'm interested in this correlation function, which is the correlation between transmission coefficients between A and B, and transmission between A prime and B prime, A prime and B prime. And I normalized all this. This means average over disorder. So I want to characterize this correlation function. Okay? So, as you said, this is a 4-point correlation function because 1, 2, 3, 4. Okay? It's not 2-point like transport that we saw before. So you are happy? Promised? I kept my promise. Good. So now I want to calculate this, and I want to calculate this with the language that we established today. So what it means that when I have quantum amplitudes, or those wave amplitudes, the multiple scattering paths of a photon, between this and this, I have to pair them in order to build either diffusion modes, incoherent modes, or modes with quantum crossings. And I want to do it systematically. This is the Lego games that we build today, right? So how is it possible to pair 4 amplitudes that we have here in order to build diffusons and diffusons with quantum crossings? So how are you to do it? So please do it, let's do it together. And then we will go for lunch, but not before. Okay, so let's see. So one way to do it, I will show you. This is one way to do it. So what I did here, I took those 2 amplitudes and I paired them in a diffusion. This is this one. So it is A, B, B, A, B, B, and the same here. A prime, B prime, B prime, and I just paired them in 2 diffusons. This corresponds to the incoherent propagation, incoherent correlations. Okay? So this gives also a contribution to speckles, but this is just a speckle distributed according to Poisson law, if you know about this. Okay? So this is purely incoherent. So what else can we build with those 4 amplitudes? First of all, is it possible to build another configuration with 2 diffusons, but that differ from this one and without quantum crossings? Is it possible? So who is in favor of yes, it is possible? Who is in favor of it is impossible. So it is possible. In order to do this, I can couple this one, A to B, and A prime to B prime, and A to B, and A prime to B prime. First of all, you notice that in order to build a diffusion, I have to couple one wave and a complex conjugate of another one. So I can couple this one with this one with this one, or this one with that one, and this one with that one. Those are the only possibilities. So if I couple now this one with that one, this is what I obtain. I obtain two diffusons, but now I have A prime, BB prime, A prime here, BB prime, which means that I have a phase shift, a phase information, but only here. Here, here, here. Okay? So now, another possibility. Is it possible to get only two diffusons now? Probably not, because the two possibilities that we have to put this one with that one and this one with that one, we did all this. So now the only other possibility is to couple trajectories with one quantum crossing. So, question, with one quantum crossing, is it possible to couple AA, BB, A prime, B prime, A prime, A prime, B prime, B prime, or not? No. No. Try it. The only possibility with the one quantum crossing is to have, so remember the rule for quantum crossing, we have to exchange the amplitudes, and you can do it only by coupling A, B with A, B that is here, okay? But A prime, B prime that is here. So here you will not have the same BB with one quantum crossing.
But wasn't the Coherent quantum crossing?
The what?
The Coherent quantum.
The Couperon, but here we are looking at 4 amplitudes, not just 2 amplitudes.
Yeah, but you could make a Coherent with one of them, and then you would have one Coherent in the first one and one diffusion in the second.
So let's do it afterwards. You will see that you cannot. This is the only possibility that you have with one quantum crossings. This is the only possibility, so I already said it. Now, with 2 quantum crossings, is it possible to build something like this without, to have A, B, B, A prime, B prime, A prime, A prime, B prime, B prime? Yes, it is possible, so it's not obvious, but here is how it works. So you can just play with it. If you have 2 quantum crossings, then you can just connect AA and BB like this. And in fact, there are the only possibilities up to 2 quantum crossings. Okay? And all this tells you what is the correlation function. And now each of those contributions have been measured. So how do you measure them? You measure them in different configurations. So what you can do in a measurement is the following. You can either measure, keep the information about A prime, B prime, or you can have an incident way along A, but you sum over all the outgoing channels, or you sum over all the incoming channels and outgoing channels, AB, A prime, B prime. If you don't sum, you have this process, then this corresponds to those 2 processes. And in fact, this angular information, you can keep it in a measurement. This is called the memory effect. And this has been measured. And this has been measured for optics. This is here. This has been measured for multiple scattering of photons by cold atoms. But this is a little bit boring because there are no quantum crossings. If you want to measure this quantity, you need 2 quantum crossings. And this gives this expression, which is just a constant. And this constant is very important. And now I'm going very, very fast because I have 30 seconds. No, I think it's not fair. You want to hear this, or you are really exhausted? You want to just to see how it works? Just to show you. But I will not say. So this is conductance. I feel uneasy because you are really exhausted. So yesterday I showed you this. You remember this this expression that the fluctuation of the conductance classically goes like L to the power D minus 4. It was written here on the blackboard. Okay, I did even a small mistake. So this was this. But now, if you have two crossing, the correction to the fluctuation of the conductance is the classical conductance divided by G squared because two crossings. Now, G squared is proportional to this G squared divided by this. It is again universal. Okay? And here, this is not universal. And this is what I told you yesterday, that the conductance fluctuations are universal. They do not decrease with the size because of those quantum crossings. I'm suffering a bit because I don't like to be so. Okay. Do I want to? They're nice, those ones, no? Just to. So this is for universal conduction fluctuations. In fact, there are 4 diagrams that gives 2 quantum crossings. They are the 4 ones. Now I claim that among those 4, 2 are diffusons and 2 are Coherents. If they are diffusons, they are insensitive to an applied Aronoff-Bohm flux. If they are Coherents, they are sensitive to Aronoff-Bohm flux because they have different phases. Okay? So by just measurement of conductance and their fluctuations, I should be able to say who is a diffusion and who is a Coherent. So here, first of all, those are the 2 diffusons and those are the 2 Coherents. If they are 2 and 2, it means that if I apply an Aronoff-Bohm flux and I measure conductance fluctuations, I should see a drop by a factor of 2. And this was the experiment that was realized several years ago in a French group by Dominique Mailly and Marc Sanquer. And what they obtained is that indeed the conductance fluctuations were reduced by a factor of 2. So what you see here are conductance as a function of the Aronoff-Bohm flux for a lot of realizations. Each trace here is a realization of disorder. Then you average over disorder. This is the average conductance. You average all this. Now the width of this are the fluctuations. And now those are the amplitude of the fluctuations as a function of the Aronoff-Bohm flux. And you see that indeed for 0 flux, the amplitude is 3, whereas for larger flux, the amplitude is 1.5. And this is a factor of 2 that comes from those 4 diagrams. Fantastic. You can do the same with spin orbit if you like spin orbit. You can do the same with Rashba scattering if you like it. You can do the same with polarization of atoms if you like it, and it works. Thank you for your attention. So again, tomorrow, now I finished with the word electrons. Finito. Tomorrow, only atoms. Atoms, superradiance, subradiance, Anderson phase transitions, and the equivalence, not the equivalence, the inequivalence between decay superradiance and Anderson transition. And then there is this colloquium, which is on completely different subject. It's on graphene, fractal spectrum, and some topology. Enjoy the lunch.
The first thing that came to mind when I saw the diagrams, it was the complex scalar field theory or something like that. Is it or
But
some
what's it? Say
more
it
involved.
this, you need a field theory. This, all this is a field theory. Yes, this
Okay.
is true.